Okay, so in that damped metamaterial class, you may have seen that once we are solving this damped wave propagation problem, you have seen that we are incorporated here like 1 minus cos mu equal to omega square m divided by 2k and then plus I omega c. So instead of k, we are inputting k plus I omega into c. So that is actually considering the damping term. Like we normally have the stiffness and then we are just adding the damping here. So with this we can get our new dispersion equation, and we have also shown that once we are solving this full thing, we can able to see that your dispersion diagram will be get changed little bit, and this portion we have seen, and we have also seen that MATLAB code of that. And also once we are doing it for the diatomic chain, we can also see that this portion, like which was very like rigidly cut to cut thing was coming, and then this one is like getting more coming into that more into that portion. Like we have done the last two things previously. So like once we are doing the machine mass metamaterial chain, now we can able to see that we have the machine mass chain. So internally, if I try to draw that one bigger, so my internal one is like M2, spring is C2, sorry, spring is K2, stiffness is C2, and then the other mass is M1, and that is connected with the K1 spring and C1 spring. Okay, so if I try to write the equation of motion for the internal, and if I think this is my V, Vn, and this is my Un, so what can I write for the internal degree of freedom? So equation of motion for internal DOF, we can get it m2 Vn double dot plus C2 Vn dot minus Un dot plus K2 into Vn minus Un, that should be equal to 0. Okay, so now if I am substituting Un equal to Un e to the power of I omega t and Vn equal to capital Vn e to the power of I omega t, then what can I write? Minus omega square m2 Vn plus I omega c2 into Vn minus Un plus k2 into Vn minus Un, that should be equal to 0. Okay, so what is my term? Omega square m2 plus I omega c2 plus k2 whole into Vn should be equal to I omega c2 plus k2 into Un. So what is my V2? My Vn can be written as I omega c2 plus k2 divided by omega square m2 plus I plus k2 minus I omega c2 into Un. So that's the conversion from like Vn can be represented in terms of Un in this format. Now if I substitute that full thing here in that for the first mass, then what can I get? So if I substitute it for the first mass, so first mass equation of motion m1 Un double dot plus k1 into Un 2 Un minus 1 plus Un minus this plus C1 into 2 Un dot minus Un minus 1 dot minus Un plus 1 dot plus K2 into Un minus Vn plus C2 into Un dot minus Vn dot, that is equal to 0. Okay, so if I substitute everything and if we do it like this way, we can able to get that. Okay, so now if we are writing it, then what we can get? Minus omega square Un plus k2 plus I omega c2 into un minus vn plus k1 plus I omega c1 into 2 un minus 1 minus un plus 1, that is equal to 0. That we can able to get. So now here what we can do, we can try to substitute whatever is there in terms of Vn, so we will get the full equation in terms of the Un. And also I hope you guys recall that once we are doing from, this is my nth cell, this is my n minus 1 cell, this is my n plus 1 cell, so once we are going here and here, we can able to implement the block theorem. So un plus 1 can be written as e to the power of I mu times un, and un minus 1 can be written e to the power of minus I mu times un. So once we can able to write that, I can write this equation as like m1 omega square un plus k2 plus I omega c2 into 1 minus, so this term I am just saying like maybe chi. So 1 minus chi into un plus k1 plus I omega c1 into 2 minus e to the power of I mu minus e to the power of minus I mu into un, that is equal to 0. So we can get minus omega square m1 plus k2 plus I omega c2 into minus omega square m2 divided by minus omega square m2 plus k2 plus I omega c2 plus 2k1 plus I omega c1 into 1 minus cos mu, that is equal to 0. So cos mu we can able to write long term 1 plus minus m1 m2 square omega to the power 6 minus m1 c1 square minus m1 plus m2 k2 m2 into omega to the power 4 plus minus k2 m1 omega square plus I omega to the power 5 c2 m2 square divided by 2 omega square c2 square plus minus k2 plus omega square m2 whole square k1 plus I omega c1. No, this is not m2, this is mt. This is also mt, this is mt, where mt equal to m1 plus m2. Okay, so if we do that way, we can get that expression. And if we see the dispersion diagrams are like previously it was going up like this, then it was going down, going like that. So this was the previous dispersion diagram. Now what happened? Now that dispersion diagram starts shifting. Instead of this, we will start having it like this way. Here also it will be going like this. So these red diagram are becoming the dispersion diagram for the damping. So we can see that the sharp boundaries are getting missed. We are not able to get those sharp boundaries, rather than the boundaries become blurred, and we are not also getting directly like as in case of the undamped, we can able to say that okay, we were having a clear boundary that there is like everything is getting propagated. Here everything is attenuated. We have a this type of very clear cut boundaries, but these type of boundaries get missed in case of these plots. Okay, so that we can able to see here. Okay, so this is the plotting style. But if you see, remember our main thing that we discussed, that we have a equation, and this equation can be solved in the two part. One is like we are solving it giving the frequency, and we try to find out what are the wave numbers, and on the other hand we are giving the wave numbers, and we try to solve what are the frequencies. So it is all falling in that portion where we are giving the excitation frequencies, and we try to see whether the wave can able to propagate in the space or not. So these all are giving the driven wave approach. So these all were the driven wave approach. But here once we are inputting the damping, then the question of the free wave approach is also becoming very predominant, and that can give a sense that how much the energy can be dissipated from that system. So let's see how that works. So like for example, in the monoatomic chain, if we see, in case of the monoatomic chain, what was the dispersion? So now we are starting to do the free wave approach. So in case of the free wave approach or driven wave approach, whatever it is, so driven or free, driven wave or free wave. So if you see, like we have a dispersion relation. So dispersion relation is basically telling like you are having like let's say cos mu equal to 1 plus or maybe 1 minus m omega square divided by k. That's a general form I just wrote it. So you see that wave number. So the left hand side is the wave number. So basically it's a relationship between. So it's a relationship between wave number, that is mu, versus our frequency, that is omega. So that's a relationship between mu and omega. So the point can come which way we are solving it. Like suppose for example, if we are giving a omega, we will give a mu. Then whatever the way we are solving, it hardly matter. Okay, so if the relationship is like 1:1, like we are giving a omega and we are getting a mu, then there is no problem. But now here what's the problem? Our omega can be means if we are inputting omega, there can be multiple mu, and that mu can also be complex. So that's create a big problem. Like once you are getting an output complex, then inputting that complex output is a big problem. So that vice versa is not very clear. So there is the issue. And so then the question can come that suppose if we are inputting, now your input is like a real mu, output will be omega. Now how many omega? how many omega, complex or not. So that things comes into picture. So therefore the complete dispersion study is divided into the two part. One is the free wave approach, where we are giving the wave number as an input, and another is the driven wave approach, where we are giving the frequency or excitation frequency as an input. So that's why it is driven wave. We are giving a driving frequency so that we are trying to see that whether the wave is propagating or not. So we are driving that wave. So it's a driven wave. Or on the other hand, we have give some sort of mu, and we try to let the structure vibrate freely. So that's the free wave approach. We are not giving any excitation or anything. We are just in free so that the waves can be able to freely propagate. Okay, so that's the two prime difference. But both the things is working on the basic dispersion relation. So that dispersion relationship is not getting changed due to the free wave approach or or the driven wave approach. That remains same exactly. The dispersion relationship remains same for both, but change happening the we are looking at, and the things what we are trying to understand from the dispersion relationship. Okay, so dispersion relationship is primarily the property of the system. Now how we can able to use that property, there actually the driven wave and the free wave approach lies. Okay, so let's see. Now let's take a dispersion relation of the damped monoatomic chain. So that will tell us that where is the difference actually lying. So damped monoatomic, So damped monoatomic dispersion is eta square minus 4I zeta into 1 minus cos mu times eta minus 2 into 1 minus cos mu, that is equal to 0. From the dispersion we can get cos mu equal to 1 minus eta square divided by 2 into 1 plus 2 into I eta omega. That was there from the dispersion relationship we can get. So now you see that once we are getting this, now this equation has an input. So this equation has an input eta and output mu, but we want opposite. Eta can be in the left hand side, or maybe we can write the equation as a polynomial of eta. Okay, so what we can do, we can take it. So this equation can be now rewritten as like first 1 minus cos mu equal to eta square divided by 2 times 1 plus 2 into I. Okay, so now we can write it 1 minus cos mu 2 times into 1 plus 2 I zeta nu equal to nu square. Okay, so nu square into, so now you see this is my second order term plus minus 2 into 1 2, it will become 4 into cos nu into I zeta eta plus 2 into 1 minus cos nu, that will be equal to 0, which is nothing but this one. There will be also minus sign, sorry, minus sign. So which is nothing but this one. So if we rearrange that dispersion relationship, we can able to get it in the new form. But now here we need to notice what, now this equation is like a quadratic in terms of eta. So what is the solution of eta? We can write eta equal to minus b minus b. So with I minus b plus minus root over of b square. B square is b square minus b plus minus b square. So with a minus will become, because I is there, minus 4ac. So 4a is 1 and c is become 8 into 1 minus cos mu. 4ac divided by 2. So this way we can get our two different values of eta. And now you see this eta, it is needless to say that it's a complex number, because already the complex number is placed here. Here you have a term like 4 into 1 minus cos mu into xi with I. So that complex number is always residing there. So therefore our eta will have this thing. Okay. So this can give me, so now here what happens, so if I tell that I am giving a wave number to that domain, then we can able to find out what will be the frequency of the vibration. Now think, what does that mean in reality? So let's think we have a string. Okay. Now what does it mean that we are giving a wave number to the system? So wave number to the system means we can think that, so what is wave number? Like wave form is there, or like some wave form is there, so that this distance is basically my wave number. That is the wavelength, and we can tell that within one unit length how many waves are there is my wave number. So can we say that we are giving a wave number to the system means we are giving that many number of nodes. Nodes means the point where we can say that the vibration will be 0. So they are basically like a equidistant from of the wave number, which are equally distant of the wave number wavelength. So we can say that that many number of nodes we are actually placing in the system, wave number of nodes we are placing in the system, and we let the system oscillate just some sort of free oscillation we have given to the system, and we try to find out what is the natural frequency of that. Then we can able to get like so then what we can get, so like we make this type of setup. Now what happens, like suppose you got that, now you just displace it and leave it. So it's like a free vibration. So we are doing a free vibration study. So like a free vibration. So in a free vibration, what are we getting? What is the output of a free vibration? In a free vibration, we can able to see that the vibration will decay slowly. So like our things will go and then it will slowly decaying. So this type of response we can able to see in case of a free vibration. So here we will have that similar type of free vibration system. So what can we able to estimate from here? So that may give us an estimation of the damping of the system, that how much damping is present in that chain, so that like if we are giving a free vibration, how quickly the system will dissipate all of its energy and it will come to rest, we can able to find that. Okay, so now think how it can able to show. Like we will get the eta, very good, so we will get eta. Now eta will be, so we will get maybe 1 value, 2 value, 3 value, or different values of eta depending on whatever the order of the polynomial we are solving. Because in the previous case, what was the order of eta? Order of eta is second order polynomial. So how many roots we should get? We will get 2 values of eta. Now the question comes whether these 2 values are real or imaginary or what. Now as I already told that these values are Means there is a complex component, definitely, and because you see that 2 zeta I portion is always staying there, okay, and then that remaining portion is coming. So this portion maybe become 0 some cases, then this will go, but still always you are having a imaginary part is always there. So it may be, or in fact some cases maybe cos mu could become 1, and then also it will become 0, so that the real part can be gone, so that the imaginary part can go, or the xi can be 0, then also it will be real. So now if we try to think, so that this form, if I write it very clearly, we can write it I into xi into delta plus minus delta times xi square delta square. What is delta? Delta is equal to 2 into 1 minus cos mu. So this is my eta. Okay. So now what is happening here? Now eta has the 2 value. So now think what eta was. Eta is nothing but the ratio of the frequencies. So eta, how we defined? Eta was defined like omega excitation frequency divided by root over of k by m. So root over of k by m is the natural frequency of the chain, and omega is the excitation frequency. So, or excitation frequency, or the frequency in which it is going to vibrate. Maybe you can find the natural frequency, or the eigen frequencies rather, you can say. So if we think that way, then once we are having this structure, and if we leave it to oscillate, what are we getting here? This we can get. So now if we think that eta is basically my ratio of my frequencies, and eta, so if I think that eta can be written as like alpha plus I beta, then what is exactly happening here? Then my response is e to the power of these into time, and no, eta is this, and if you think my response is e to the power of I omega t. Now omega is basically some scaled times eta. So can I say that my response is becoming e to the power of I times maybe some factor like omega n times eta times t. So e to the power of I. So now omega just I'm just taking it as like some number. So I times eta. So it will become I alpha minus beta times t. So we can see that e to the power of minus beta omega n times t into e to the power of I omega n alpha t. So e to the power of I beta t. So what e to the power of I beta t will do? E to the power I beta t will actually decay. E to the power I beta t will actually decay the full response in the time domain. So this beta means the imaginary part of the wave of the frequency is nothing but responsible for the dissipation or the damping. Okay, so if we are considering a single degree freedom system having mass m, stiffness k, and damping c, we can able to write it mx double dot plus c x dot plus k x, that is equal to 0. Now I can assume x equal to e to the power of I omega t into x. So small x equal to e to the power of I omega t into x. In that case, I can write it minus omega square m into x plus I omega c into x plus k into x equal full thing into e to the power of I omega t equal to 0. Okay. So now if we can able to write it like that, then this portion should be also always equal to 0. So minus omega square m plus I omega c plus k, that is equal to 0. So what will be my omega? My omega will be minus IC plus minus root over of p square. So minus c square plus b square minus 4ac. So minus 4ac. So minus is becoming, because this is plus, this divided by 2a. So now if this is the scenario, now I can think like c equal to 2 xi omega n into m. Okay, so first term is coming c divided by 2m into I plus minus, and so this is the scenario. So c square plus 4mk can be written as 4 xi square omega n square m square plus 4 into m square omega n square. So I can write it 4, yeah, there is a minus sign. So 4 omega n square m square into 1 minus zeta square. So I can put it here, 2 into omega n into m divided by 2m with a minus sign, 1 minus xi square. Makes sense? So cancel out, 2 cancel out, and m equal, and c by 2m. So c by 2m is also xi into omega n. So I can write it xi into omega n into I plus minus omega n into root over of 1 minus xi square. Okay. So what is the response now? Response will be to the power of I times xi omega n t plus minus omega n root over of 1 minus xi square times t. So I can write it e to the power of, yes, there is a I. So minus xi omega n t into e to the power of I omega dt. What is omega d? This is omega d, that is the damped natural frequency. So we can see that in case of a single degree freedom system as well, this term is my dissipation term, which is decaying, that is xi into omega n. So now xi into omega n is coming from where? Once we are writing this as like e to the power of I omega t, then omega is written like plus minus alpha minus I beta or plus I beta. So omega is written like this way, that plus minus alpha plus I beta. So in that case we can see that this beta is basically denoting my dissipation. Now here also, now if we think similar concept, if we think here that beta into omega n, that beta into omega n is showing the decaying energy. So this is nothing but our damping. So this way that beta is actually showing how the dissipation of the system is happening. So we can write it like that, that damping psi d can be written as imaginary of nu in terms of mu divided by mod of mu. So that gives me that xi d, so which is the dissipation, and this is also, it becomes a function of mu, and we can get that eta d, which is the damped natural frequency, that is nothing but real part of the frequency. And so this way we can actually able to estimate how much is the damping, and this damping is not a single number, that will be changed with my wave number. We can able to see that how that damping value is getting changed. So we can able to see that way. So this varying damping ratio with respect to the wave number we can able to find out here. Okay, so that's one of the very unique property we can able to see once we are studying the wave number, we can able to find it. And that makes sense as well, because you can think that if you are changing that distance between the nodes, our dissipation amount will be getting varied. So that is represented from here. Okay, so with this you can close it here.